Let's go! Number 5. Reality shouldn't have snap settings. Yet in one of the cleanest lab discoveries ever, it does. And if we were in a simulation, this is exactly the kind of thing you'd expect to find. Stable, allowed values, like the engine has built-in rails. In 1980, physicist Klaus von Klitzing was studying electrons trapped in an ultra-thin layer, basically forcing them to live in a two-dimensional world. He cooled the system to cryogenic temperatures, cranked up a strong magnetic field, and measured what's called the Hall resistance. If the universe were a smooth, analog place, that resistance should drift as you turn the magnetic field knob. But the meter didn't drift, it climbed, and then it locked. Flat plateau, change the field more, still flat. Then snap, another plateau. Like reality had a staircase hidden under the carpet. Even better, those plateaus were so stable that metrology labs, places like NIST and their equivalents around the world, could use the effect as a practical calibration standard. Physics has a solid explanation here. In strong magnetic fields, electrons fall into discrete energy states called Landau levels, and the stability of the plateaus is protected by topology. Basically, a built-in robustness that doesn't care much about messy imperfections. Yet the eerie feeling isn't we don't know the math. The eerie feeling is what it suggests. Underneath the continuous world we experience, the universe sometimes behaves like a system with approved values and hard boundaries. If you wanted a reality that doesn't glitch when it gets noisy, you'd build it exactly like that. It's like dragging a smooth volume slider on your phone. It looks continuous. Your finger moves fluidly, but under the hood, it's clicking through steps. The quantum Hall effect is like catching reality, doing that in the open, and realizing it was never obligated to look so digital. So if the universe has these snap points, we can measure in a lab what other snap points are hiding in plain sight, waiting for the right experiment to reveal them. Number 4. Now we move from digital steps to something more unsettling. The feeling that the universe waits for your question before it decides what the story even is. And in a simulation? That would be efficient. Don't render what the player didn't ask to see. This is the delayed choice family of experiments, first proposed by John Wheeler and later built in modern photonics labs using single photons, interferometers, and ultra-fast switches like electro-optic modulators. Picture a Mach-Zehnder interferometer. A photon hits a beam splitter, and now it has two possible paths. If you recombine the paths, you get interference, the wave-like pattern that screams, "It behaved like it took both." If you don't recombine them, and you measure which way it went, you get particle-like behavior. One path, one detection. Here's the twist. In delayed choice versions, the decision to recombine or not can be made after the photon has already entered the device. In some implementations, it's made so late that any normal, tiny ball story collapses, and yet the statistics obey the measurement you chose. Choose interference, you see interference. Choose which path, you get which path. The outcomes line up with quantum theory, as if the photon politely waited for your final decision before committing to what it was. Mainstream physics doesn't say the photon time traveled. It says the photon wasn't carrying a single classical history at all. The measurement setup defines what kinds of facts can exist. Complementarity says wave-like and particle-like aren't identities the photon wears like outfits. They're answers to different questions. Still, even if the equations stay calm, your intuition doesn't, because it feels like the universe is refusing to write the middle of the story until you decide which genre you want. And if reality were simulated, render on demand is basically the oldest trick in the performance optimization book. It's like you send a message that could be read as a joke or as a serious threat, and only after it's delivered, you decide which interpretation counts, and the universe rearranges the context so you're technically correct. In real life, that's called gaslighting. In quantum labs, it's called measurement. So here's the question. When no one asks the question at all, is reality fully written or just waiting in draft mode? Number 3. Okay. This one is the classic sign that the universe is running something deeper than common sense. Entanglement, tested by Bell experiments. And if we were in a simulation, these correlations would look a lot like a system enforcing consistency across the whole map, not like tiny objects carrying private little secrets. In 2015, at Delft University of Technology, Ronald Hansen's group ran a landmark test using electron spins in diamond defects called NV centers. They created an entangled link between two qubits separated by about a kilometer, made rapid and independent measurement choices, and recorded outcomes across many trials. The point was to remove the usual escape routes, those loopholes where skeptics can say maybe they signaled or maybe the sample was biased. And the result was not subtle. The correlations violated a Bell inequality, which means you can't explain what happened using any theory where each particle carries a pre-written answer sheet and nothing influences anything faster than light. It's not they matched sometimes. It's a very specific pattern that beats every local hidden variable model. Quantum mechanics stays annoyingly composed about it. It says, the pair is described by one shared state, and measurement outcomes aren't fixed in the classical way until measurement happens. And no, you can't use it to send messages faster than light. These are correlations, not controllable signals. But none of that fully removes the chill, because the universe is basically telling you, distance does not guarantee independence the way you thought it did. If a simulated world needed to stay internally consistent for every observer, you'd expect exactly this kind of global bookkeeping. If this were a sitcom, it would be two twins separated into different cities. No phones, no cheating, and yet every time you ask them questions at the same instant, their answers line up with a pattern too perfect to hand-wave away. You can't accuse them of texting. You can only accuse the universe of being coordinated. So what else in your life feels random only because you can't see the hidden coordination? Number 2. Now we go after something even more personal than distance. The idea that facts are universal. And if simulations are good at anything, it's this. Different observers can have locally consistent experiences without there being one master screen that everyone shares. Wigner's friend is a thought experiment where one observer measures a quantum system inside a lab and records a result, while an outside observer treats the entire lab, friend included, as a quantum system. The tension is brutal. The friend thinks the outcome is definite. The outside observer can, in principle, perform a measurement that tests whether the inside lab was still in a superposition. In 2019, a widely discussed photonics experiment led by Massimiliano Proietti and collaborators built a version of this logic using entangled photons and nested measurements. The details get technical fast, but the headline is simple. Under a set of assumptions that sound totally reasonable in everyday life, single outcomes, observer-independent facts, and locality, the experimental statistics clash with what those assumptions would predict. Measured result: the correlations exist. That part is real. Interpretation. What it means is debated. Some interpretations say outcomes branch, many worlds. Others say facts are relational, defined only relative to interactions. Critics argue about the strength of the assumptions and whether these lab versions truly capture a friend with a definite record in the way the thought experiment imagines. But even with all that caution, the vibe is unavoidable. Quantum physics keeps suggesting that facts might not be a global spreadsheet the universe keeps for everyone. They might be more like local receipts that only become mutually consistent when systems interact and compare. That's not proof of a simulation. But it's exactly how you design a scalable system. Local truth first, global reconciliation later. It's like two people watching the same live event on different streams. One is delayed differently. Both swear they saw what just happened. Neither is lying. The system itself doesn't offer a single shared timeline until you sync up. In our world, that's buffering. In quantum mechanics, it might be fundamental. So if facts can depend on how you're connected to the system, who exactly is reality written for? Number 1. And here's the big one, the most simulation-flavored sign, because it suggests reality might be made of information, not stuff. Like the universe isn't a stage filled with objects. It's a data structure with rules. And if you were building a simulation, information limits wouldn't be a weird side effect. They'd be the entire point. This idea starts with black holes, where physics basically tripped over its own shoelaces and discovered something terrifying. In the 1970s, Jacob Bekenstein argued that black holes should have entropy, meaning they store information. Stephen Hawking's work then tied black holes to temperature and radiation, And suddenly black holes weren't just cosmic vacuum cleaners. They were thermodynamic objects. The shock was how the information scales. Not with volume, the way you'd expect if you were storing stuff in a box. It scales with surface area. In plain words, it's as if the maximum information inside a region is written on the boundary, like the universe is saving the file on the edge of the screen instead of inside the scene. Then came the holographic principle, ideas pushed by Gerard 't Hooft and Leonard Susskind in the 1990s, suggesting that a full 3D world could be described by information on a 2D surface. Later, in 1997, Juan Maldacena proposed a very famous mathematical duality, a DS/CFT, that made holography feel less like poetry and more like a working machine. Two wildly different descriptions, one inside and one on the boundary, giving the same physics. Here's what experiments actually show versus what people interpret. The measured layer is that black holes exist and behave consistently with general relativity, and the thermodynamics framework is one of the most successful cross-checks in theoretical physics. The interpretation layer, this is important, is that holography is a deep organizing principle, not something we've directly measured as the universe is literally a hologram. It's powerful, it's debated, it's not consensus as a literal claim about everyday spacetime. So why does this belong in a simulation countdown? Because if reality really does have a maximum information capacity, and if the most efficient description lives on boundaries, that sounds disturbingly like a computational constraint. It sounds like optimization, like memory management, like the universe is saying, you don't get infinite resolution, you get what fits. Real-life analogy. Imagine a massive open-world game where the entire world state is tracked by a smaller set of rules and boundary conditions, and the rest is generated consistently from that. You're not storing every blade of grass as a unique object. You store the recipe, the constraints, and the seed, and the world appears. Holography is that kind of vibe, but written in serious mathematics instead of a game engine. So here's the haunting question to end on. If the universe has an information budget, what happens when we finally find the edge of the memory limit? And that's the countdown. Click that subscribe button for more quantum stuff.